Okay, we're going to talk through a little bit between E1 and E2 for the last part of Monday and Tuesday's SI. All right, so just a few examples up here, and we're going to use the rules that we learned a couple videos ago about E1 and E2 and decide, which one would be more likely to go through with these reactions. Okay. So our first example, try these, pause the video, review the last part if you need to, use your book to help. There you go through it, answer these 6 problems, see how you do, and then talk about it, okay? All right, this first example here, what do I see? I see I have a very good leaving group of iodine in the primary position, okay? So that's a pretty good indication that I'm probably gonna do an E2 reaction. Well, E2 favors actually all of them. That'd be more like an SN2 thing. So the primary isn't exactly telling me a lot about E1 or E2. The good leaving group is that E2 would likely, would be more likely at this point, only because E1, remember our rate determining step, but that leaving group has to leave all by itself. So a strong base to remove a beta hydrogen and add a double bond here, the leaving group leaves all in one step would favor an E2. Okay. I have a pretty strong base here in ethoxide, okay? Now I do have a polar protic solvent, but notice, if my base interacts with that polar protic solvent, okay, and takes that beta hydrogen, and I'm gonna draw that back, takes that hydrogen here, now this becomes ethoxide, and this becomes our solvent. So we didn't really change anything by doing that. So yes, we have a polar protic solvent, but it's not going to interfere with our base, because when it does, we make just as much base as we do solvent there, okay? So notice that going forward, if you have the conjugate base of an acid, or conjugate acid of a base, vice versa, as your solvent and your reactant, they're just going to cancel out, and it doesn't matter whether it's polar protic or polar aprotic, okay? All right, so I do have a good leaving group, that makes me think E2. I have a strong base, that makes me think E2. And I know that this isn't really gonna interfere with it much, okay? So I can say that this is likely E2. Okay, and my final product would look something like that, okay? Sweet. All right. Next example, I have a good leaving group in a secondary position, and I have a strong base here, OH minus. Okay, we can get rid of that spectator ion. Okay. E2. Not given the solvent. I have a strong base. Strong base is going to favor E2 in the secondary position. My major product here would be this, okay? More substituted alkene there. And then I could also say, I could get the Z conformation, okay? Here I can't draw the Z conformation. I just have that one. But here I could also draw that conformation there if I wanted to. This would be the most stable product. Our E alkene, I would say this is also E2. Okay. Move down to the next example. Okay. I have a primary bromine here. Again, that's likely going to favor E2, only because I know E1 would be difficult to make a carbocation there. Terbutoxides are pretty strong. I can get rid of that K there, and you can just think of this as an RO minus group. Same as up here. I'm not given the solvent, okay? Terbutoxide is going to be a little bit funky in the future, okay? Because it's so bulky, you're not always going to get the most substituted alkene. You're actually going to get what looks like to be the more unstable alkene as your major product. This example doesn't allow you to do that, which is why I'm using it here. Right now, we're just at a point where I see terbutoxide as a strong base, and so this is going to be E2. Pretty straightforward, okay? All right, here I have a tertiary group here with my leaving group. Okay, so it's going to favor E1, right? And not only that, I have a weak base that would also favor E1 and a polar protic solvent. All of these are telling me E1. This one's really going to be big E1. Okay. Again, I'm not really asking you to draw the products. We could have multiple products here and maybe perhaps looks like conformations. We don't need to do that right now. I'm just asking which one's going to be favored. All right. Now here, I have a leaving group, bromine, secondary position. All right. This is not OH, so this isn't a strong base. This is just an alcohol. That would be a weak base. I'm not given a solvent. I'm not really provided a solvent here. So alcohol is a weak base. OH is a strong base, but alcohol, okay, is a weak base, secondary position. I would say this one is also E1. And just like before, these can also go through under substitution. This one I know can go under will undergo substitution to a certain degree. This one would have as well, I believe. I don't know the steric hindrance on that one. This one likely. Maybe if we had something else to take the hydrogen off, we could do nucleophilic substitution there as well. Main point is like, just because we're deciding between E1 and E2 doesn't mean these can't be substitution. Right now, we're just starting off, we're just doing E1 and E2. Last example here, secondary alcohol. I don't have a very good leaving group, okay, but I do have a concentrated acid in solution. If you notice, this is almost a carbon copy of question number 9 in the last assessment. Just because we have a bad leaving group doesn't mean it has to stay a bad leaving group. We have sulfuric acid here that can donate a proton to this alcohol, making it water. And if you remember in that question on number 9, it said concentrated hydrosulfuric acid can react with the provided alcohol in an E1 mechanism. Okay. So again, alcohol here would take, and it would actually be bonded to oxygen, can take a hydrogen, that becomes water. I'm doing all this in one step. You'd have to draw reaction arrows. I don't want to do that. This becomes water, and then it leaves, giving us a carbocation. And if we know we have a carbocation, we must be in E1. We aren't actually provided water here, so we know that HSO4 minus is going to be our base that then deprotonates, and our major product would be here, so we're more substitute. Okay, getting rid of that carbocation. Cool. And we don't need an E or Z conformation because this side is the same. This one would also be E1. Okay. Cool. This is like the same problem that was on number 9 in the last assessment there. I had a secondary group. I had sulfuric acid is a strong acid, meaning the conjugate base is weak. Okay, so it helps us conclude that it's going to be an E1 reaction. We also made a good leaving group. We know that water had to leave in this case, okay, because we had a weak-ish base with HSO4 minus. Weak base tells me E1 reaction, okay? All right, I think this will prepare you for Monday's class. We'll have SI on Wednesday right after and kind of cover some stuff there. I'll have a little bit better idea as well what Dr. Andrews is gonna want to cover on Monday. But hopefully these videos kind of help start our ability to rank SN1, SN2, E1, and E2. Don't remember, you can. I wouldn't recommend memorizing that whole list of strong bases and strong nucleophiles. Instead, go over the rules like those on the left here with E1, E2. Those are probably going to be more helpful. And also, there's only so many bases and nucleophiles that are thrown around. Give it about a week, and I think you're going to get pretty used to recognizing strong nucleophiles and strong bases. So I'll see you all Wednesday.